Hi everybody, it's Professor Mitchell. We are finishing up Chapter 9 today, talking about conducting a hypothesis test for a proportion using the p-value approach. And that goes along with the assignment of the same name. Our objectives in this section are to determine the p-value for a hypothesis test for proportion and make a conclusion and interpret the results for a hypothesis test for proportion using the p-value approach. So to perform a hypothesis test for a proportion, we need to work through the following steps, which you've heard about many times before. First, choose the null hypothesis and the alternative hypothesis. Then decide on the significance level, alpha. Compute the test statistic, which for a test about a proportion is z. We write the calculated test statistic as z sub 0. And then you have two choices for what to do next. You can either find the critical values to either reject or fail to reject the null hypothesis, or what we'll be talking about in this section, use the p-value to reject the null hypothesis or fail to reject the null hypothesis. And then finally, we always want to interpret the results of the hypothesis test. After the null and alternative hypotheses are chosen, the significance level is decided upon, and the test statistic is computed, we need to then compute the probability value, usually known as the p-value. This is the probability of obtaining a sample statistic as different or more different from the parameter specified in the null hypothesis as the statistic obtained in the experiment. The probability value is computed, assuming the null hypothesis is true. The p-value is the area of the shaded region under a normal curve, and therefore p-values depend on whether the hypothesis test is left-tailed, right-tailed, or two-tailed. Here are the steps needed to calculate the p-value for a hypothesis test for a proportion. First, determine if the hypothesis test is left-tailed, right-tailed, or two-tailed. First, calculate the value of the test statistic. If the hypothesis test is left-tailed, the p-value will be the area under the standard normal curve to the left of the test statistic z sub 0. If the test is right-tailed, the p-value will be the area under the standard normal curve to the right of the test statistic z sub 0. And if the test is two-tailed, the p-value will be the area to the left of negative absolute value z sub 0 plus the area to the right of absolute value z sub 0 under the standard normal curve. Now that last one is a little hard to understand without a picture, especially the way they said it. Basically, it's the area that lies more than z sub 0 standard deviations away from the mean. Okay. I oversimplified it just a little bit with that explanation, but that's basically what it is. But there is a picture coming up, and that'll make it a lot easier to understand. Additional details are shown, and the diagrams will provide a visual explanation to help identify the p-value as the corresponding area under the standard normal curve. Note that to find the areas referenced on the next few slides, a table of areas under the standard normal curve may be utilized. We call that table A2. So here's the picture for a left-tail test. Usually, but not always, with a left-tail test, the calculated test statistic will be negative. However, what is always true for a left-tail test is that the p-value represents the area to the left of that calculated test statistic. So this is kind of the simplest situation because remember in table A2, it gives you the area to the left of the z-score that you look up. So generally your p-value will be found right in the table and you don't have to do anything with it. All right, a right-tailed test is almost that simple, usually, but not always. The calculated test statistic for a right-tailed test will be positive. And the p-value represents the area to the right of that calculated test statistic. So this is the situation where you have to look up the z-score in the table and then subtract the area in the table from 1. And then finally, this is the kind of confusing one from a few slides ago. For a two-tailed test, the p-value is equal to the probability of observing a value of the test statistic that is at least as large in magnitude to the actual observed value. So, for example, what that means is if your calculated test statistic came out to negative 2.3, that means at least 2.3 standard deviations away from the mean in either direction. All right. So when they write negative absolute value z sub 0, they're basically just saying take the plus and minus of your calculated test statistic, find the area to the left of the minus and the area to the right of the plus, and add them together. All right. Now, because these two z-scores will always be opposites, what you can do instead, which is a little simpler, is just take the area to the left of the negative one and double it, multiply it by 2. All right, so here's an example. A researcher is interested in testing the claim that the proportion of shoppers who use coupons while shopping is at least 20%. To test this claim, the researcher collects data on a sample of 500 shoppers and determines that 89 of the shoppers use coupons. Based on this data, calculate the p-value corresponding to this sample data and round your answer to 3 decimal places. So they've given me the part of the table that I'm going to need. Okay, I don't know that this is the part I need until I calculate my test statistics, so that's coming up. The proportion of successes is p hat, which is 89 over 500. That comes out to 0.178. And then the test statistic is calculated as follows. Now, we used this formula in the last video. However, I wrote it just a little differently. Underneath the square root, instead of writing p sub 0 times 1 minus p sub 0, I wrote p sub 0 times q sub 0. That means exactly the same thing. Okay? I didn't realize that they were going to use this version of the formula in this section. All right, so that looks like this, 0.178 minus 0.2, and then divide by the square root of 0.2 times 1 minus 0.2, divide by 500. You should plug that formula into your calculator and make sure you get the same value. It should come out to about negative 1.23. Since we have calculated the test statistic, we can now proceed to find the p-value for this hypothesis test. Using the test statistic, and since the hypothesis test is a left-tailed test, I want to take a moment to explain why this is a left-tailed test. We're going to have a very similar example a little later. Notice that the claim is that the proportion of shoppers who use coupons is at least 20%. Now, at least means greater than or equal to. So the opposite claim would be that the proportion of shoppers who use coupons is less than 20%. So you take those two relations, at least and less than. The one that includes equality is the null hypothesis. So this claim that P is greater than or equal to 0.2 would be the null hypothesis. The alternative hypothesis would be that P is less than 0.2, and that less than sign is what makes this a left-tailed test. Since this is a left-tailed test, the p-value will be the area under the standard normal curve to the left of the test statistic of negative 1.23. And using the standard normal curve that they gave us a couple slides ago, you know how to use this. There's negative 1.2. You go over to 0.03 on top, and I find that the area to the left of negative 1.23 is 0.109. What that means is that if the proportion of shoppers who use coupons really is exactly 20%, the probability of finding a sample with a proportion this low, 89 over 500, the probability of getting a sample that low would be about 0.109. Okay, so there's almost an 11% chance of getting a sample like that. All right, so that's an example for determining the p-value. Here's another one. Cat owners are more likely to be female than male. I take exception to that statistic. A random sample found 13,173 cats had female owners out of 25,468 cat owners. The sample proportion of female cat owners is therefore 0.5172. That's found, you'll see that on the next slide, but that's from doing 13,173 over 25,468. Is this sample evidence that more cats have female owners than male owners in the entire population? And we're going to use a significance level of 5%. So there's the calculation for p hat. And then for the test statistic, I just used the same one I used in the last video. P hat is 0.517. The hypothesized population proportion is 0.5. The claim is that more cat owners are female than male, all right? So that if P equals the proportion of cat owners who are female, the claim is that P is greater than 0.5, all right? So that same proportion goes down here and also here because 1 minus 0.5 is 0.5. And you work that all out and it comes out to about 5.50. So this p-value would be the area to the right of z equals 5.50. So let's take a look at table A2 here for a second. If I went to look for 5.50 on the positive side of the table, I'm not going to find it because they only list z-scores up to 3.5. Okay. So what we say about the p-value, if we're using the table, well, this means that the area to the left of 5.5 would be greater than 0.9999, which means that the area to the right of 5.50 would be less than 0.0001. All right, that's how that works. All right, so that's why I say here my p-value is less than 0.0001. If it's true that exactly half of cat owners are female, the probability of having this many female cat owners in a sample of 25,468, that probability would be less than 0.0001. So because that's so unlikely, the more likely scenario is that the proportion of female cat owners is higher than 0.5. Because the p-value is smaller than the significance level, alpha equals 0.05, we can reject the null hypothesis. Okay, remember when p is low, the null must go. So in this case, p is very low. We would say there is sufficient evidence to conclude cats are more likely to have female owners than male owners in the entire population at the 0.05 significance level. But again, some very proud male cat owners out there. All right, and then in terms of making a conclusion and interpreting the results, first we have a review of all the steps to doing the hypothesis test. We are now at step 5. interpret the results of the hypothesis test. After the null and alternative hypotheses are chosen and the significance level is decided upon, the test statistic is computed and the p-value is found. The last step in performing a hypothesis test for a proportion is to either reject or fail to reject the null hypothesis and interpret the results. All right, so here is the, if p is low, the null must go. If p is high, the null will fly. All right. If the p-value is less than or equal to the given significance level, that's if p is low, then the null hypothesis should be rejected. The null must go. Okay. Otherwise, if p is high, meaning if p is greater than alpha, fail to reject the null hypothesis. If p is high, the null will fly. The p-value is also known as the observed significance level. So the p-value of a hypothesis test is the smallest significance level at which the null hypothesis can be rejected. Therefore, if the probability or area under the curve is less than alpha, then the null hypothesis should be rejected. However, if p is greater than alpha, we should not reject the null hypothesis. And remember, when you do not reject the null hypothesis, it doesn't mean that you should believe the null hypothesis is true. It simply means that the sample data have failed to provide significant evidence to cast doubt about the truthfulness of the null hypothesis. Most scientists will find the results inconclusive. Okay? So again, it's like the difference between the defendant is not guilty versus the defendant is innocent. We say the defendant is not guilty because the prosecutor failed to make their case that the defendant is guilty. Okay? Defendant could be guilty, it's just the prosecutor wasn't able to prove it. When we have made a decision about the null hypothesis, it's important to write a thoughtful conclusion about the hypotheses in terms of the given problem scenario. And I believe this is about the fourth or fifth time you're seeing this now. Remember, the way that you word the claim depends on whether the claim is the null hypothesis or the alternative hypothesis. On this slide, the claim is the null hypothesis. So the conclusion should either be reject the null hypothesis, which means there is enough evidence to reject the claim, or fail to reject the null hypothesis, which means there's not enough evidence to reject the claim. However, if the claim is the alternative hypothesis, then rejecting the null hypothesis means the conclusion is there is enough evidence to support the claim. Or if the decision is to fail to reject the null hypothesis, the conclusion is that there is not enough evidence to support the claim. All right. Well, this example sounds really familiar. It's the same example with the coupons from earlier. They've just, dressed it up in a different story. A researcher is interested in testing the claim that the proportion of her fellow employees who bike to work is at least 20%. To test this claim, the researcher collects data on a sample of 500 employees and determines that 89 of the employees bike to work. Based on this data, the p-value corresponding to this sample data is 0.109, so that's exactly the same p-value that we found in the coupon example. Actually, when I was preparing this PowerPoint, I didn't notice that. And so I think I explained, again, where that 0.109 comes from. Right. Use a 5% significance level for this hypothesis test. Based on this p-value, interpret the results and come to a conclusion for this hypothesis test for a proportion. So the first thing I did was I stated my null and alternative hypotheses. Notice the claim is that the proportion is at least 20%. So once again, at least includes equality. So that has to be the null hypothesis. And then the alternative hypothesis would be p is less than 0.2. That less than makes this a left tail test. The p-value is 0.109. Okay, so actually I didn't show my work again for that. It's the same, remember, same exact numbers as in the coupon example. We then compare the p-value to the level of significance to come to a conclusion for this hypothesis test. So in this case, the p-value, 0.109, is greater than the level of significance. So in a world where exactly 20% of people bike to work, the probability of finding a sample of 500 people where 89 bike to work is almost 11%, all right? So it wouldn't be too unusual for that to happen by chance. That is not strong enough evidence against the null hypothesis. So because the p-value is greater than the level of significance, we're going to fail to reject the null hypothesis. And the way that we're going to write our statement interpreting that is, since the original claim became the null hypothesis, this means that there is not enough evidence to reject the claim that the proportion of employees who bike to work is at least 20%. Yes, for this sample, it was a little lower than 20%, but not enough lower that we would conclude the population proportion is less than 20%. All right, here's another example. Suppose the governor of a state claims that at least 80% of the state's 1 million residents would like him to run for another term. 100 residents are surveyed using simple random sampling, and 73% think the governor should run for another term. Based on these results, should we reject or fail to reject the governor's hypothesis? And again, we'll use a significance level of 0.05. So again, I wrote the hypotheses. This one's very similar to the last one. The claim is at least 80% want to see him run again, so that at least makes that the null hypothesis. It includes equality. The opposite would be p is less than 0.8. All right, p hat is 0.73. They were kind enough to give it to us as a percentage. 73% becomes 0.73. So now we'll calculate our test statistic. P hat minus P0 would be 0.73 minus 0.8. And then we would divide that by the square root of 0.8 times 0.2 divided by 100. So again, try this one. Make sure you get the same thing out of your calculator. I got negative 1.75. So let's talk one more time about how to get this p-value. If I go back to table A2 and I look for z equals negative 1.75, there's negative 1.7. I go over here to 0.05 and I get a p-value of 0.0401, which I went ahead and rounded to 0.04. All right, so since that 0.04 is less than the significance level, which is 0.05, okay, I just wanted to tidy up a little wording that got past me on this part. Since the p-value 0.04 is less than the significance level, p is low, the null must go. So we would reject the null hypothesis, which means there is sufficient evidence to reject the governor's claim that at least 80% of the state's residents would like to see him run for re-election. And that's going to take care of this video, and that's going to take care of Chapter 9. We'll see you next time.